Hello everyone, in this video we're going to talk about Euler path and Euler circuits. And before we go into the details of the definitions for Euler path and Euler circuit, I want to bring up a very interesting example about the 7 bridges of Königsberg. So the town of Königsberg is separated by a river, and this is the river. And on the river there are 2 islands, island A and island D. And there are 7 bridges connecting the island to the 2 banks of the river and to each other. So there's 1, 2, 3, 4, 5, 6, and 7 bridges. So the question is that whether it was possible to start at some locations in the town and travel across all the bridges once without crossing any bridge twice and return to the starting point. The problem is proposed and was solved by a mathematician called Leonhard Euler. And in his solution published in 1736, maybe one of the first use of graph theory in solving this type of problem. And in his paper, Euler studied this problem using the Monte graph, obtained when the 4 regions are represented by vertices and the bridges by edges. So you're going to indicate that this is one node or one vertex, this is another vertex, this is another vertex, and this is another vertex. So you have one vertex for C, one vertex for A, one vertex for B, and one vertex for D. So there are 2 bridges connecting A and C, so I use 2 different edges to connect A and C. There are 2 bridges connected A and B. I'm going to do the same thing here. One bridge connect between A and D, so you do this. One bridge connects D and C, so you do this. And there's one bridge connect B and D, so this is the graph representations of the 7 bridges of Königsberg problem. So I want to know this is the Monte graph model of the town of Königsberg. So the question is it possible to plan a walk so that you cross each bridge once and only once? So is it possible to plan a walk so that you cross each bridge once and only once? Now, to answer this question, we're going to dive into the definitions of Euler path and Euler circuits, and also we're going to look into Euler path and circuits theorem. All right, so for first definition is the Euler path. So an Euler path in a graph G is a walk in G such that every edge is used exactly 1. So an Euler path in G is a walk in G such that every edge is used exactly 1. Now for Euler circuit definitions. So an Euler circuit in G is an Euler path that starts and ends at the same vertex. So an Euler circuit in G is an Euler path that starts and ends at the same vertex. Now I'm going to look into some example. So this is an example of a graph that has an Euler path. So similar to the last video, when you write the Euler path or Euler circuits, there may be multiple solutions to one problem. What I'm going to present to you is just one of the solutions. So one Euler path for this graph is going to be So one Euler path for the graph is, so you're going to start with F, and you're going to go to A, then go to B, then go to C, then go to F again, then go to E, then go to C, then you go to D, then finally you go to E. So this Euler path travels every edge once and only once, and start and end at the different vertices. So I want to note that this Euler path travels every edge once and only once, and starts and ends at different vertices. Now I also claim that this graph cannot produce an Euler circuit, since no Euler path can start and end at the same vertex without crossing over at least one edge more than once. Later on, when we look at the theorem of Euler path in Euler circuit, you will see what I mean by that. And also, you will see why I need to start at F instead of at A, B, C, and D. You can also start at E. Again, you will see the reasons why you can choose either E or F to start the Euler path. For Euler circuits, it doesn't matter where you really start. Again, you will see that in the theorem. I want to again emphasize the path that we already cover in here, that you start at F and you follow along path E1, and then to go to A. From A you follow the path E2 to go to B. From B you follow E3 to go to C, then E4 to go to F, and E5 to go to E, E6 to go to C, E7 to go to D, and E8 to go to E. So there are 8 different edges, and we only travel every edge once and only once. So here is E1, here is E2, here is E3, here is E4, this is E5, this is E6, E7, and E8. Alright, so therefore this is an Euler path. That is because the Euler path travels every edge once and only once, and the start and ends at the different vertices. Alright, in the next example, we're going to see another graph, and this graph is about Euler circuit. So this is the graph for Euler circuit. So of course, again, there's multiple solutions to this particular graph to get the Euler circuit. So one of the solutions is going to be that one of Euler circuit is, for this particular case, I'm going to start at E. So E, you go to A, then go to B, then go to F, then go to E again. From E, you go to back to F, and from F you go to D. From D you go to C, and from C you go back to E. Going from E to A, you follow the edge E1. From A to B, you follow the edge E2. From B to F, you follow edge E3. From F to E, you follow edge E4. Now going from E back to F, you follow this edge E5. From F to D, you follow the edge E6. From D to C, you follow the edge E7. And from C to E, you follow edge E8. So this is E1, E2, E3, E4, E5, E6, E7, and this one is E8. So this Euler path travel every edge once and only once, and start and ends at the same vertex. So this is called the Euler circuit. So this Euler path travels every edge once and only once, and starts and ends at the same vertex. So therefore the conclusion is that you have an Euler circuit. Again, there should be multiple solutions to this Euler circuit, right? You can start at E, you can start at A, you can start at B, you can start at F, D, or C. You should get the similar results that represent an Euler circuit. Now, how can I know where to start on the Euler path or Euler circuit? And how could I, by looking at the graph, identify if it has an Euler path or Euler circuit? That lead me to the theorem of Euler path and circuits, or Euler path and circuits theorem. So in this theorem, it say that a graph G has an Euler circuit if and only if the degree of every vertex is even. So a graph G has an Euler circuit if and only if the degree of every vertex is even. Now that is for Euler circuit. For an Euler path, so a graph G has an Euler path, but not an Euler circuit. If and only if it has exactly two vertices of odd degree. Okay. Now, what is the degree of a vertex? Right. So the degree of the vertex is the number of edges coming from that vertex. So I want to mention one thing here: degree of vertex. Degree of a vertex is the number of edges coming from that vertex. Okay, now go back to the two examples that we just did to see how can we recognize if there is an Euler path or an Euler circuit by just looking at the graph. Okay, for the first graph, we note earlier that in the example this is an Euler path, and for this graph there's an Euler circuit. Okay, so how can we know? We calculate the degree of each vertex in the graph. So for the vertex A, there are two vertex coming from A. Therefore, the degree of A is going to be 2. The degree of B is also 2. The degree of C is going to be 1, 2, 3, 4. So the degree of C is 4. The degree of D is 2. The degree of E is going to be 3 because you have 1, 2, 3 different edges coming out of E. And for F, there's also 3. So 1, 2, and 3 edges coming out of F. So the degree of F is going to be equal to 3. By the theorem, it say that a graph G has an Euler path if and only if it has exactly two vertices of odd degree. So in this case, you have two vertices with odd degree. So this vertex F and this vertex E. Okay, so you can conclude that since there are exactly two odd degree vertices, the graph has an Euler path. Alright, and also I want to answer the question is where do you start on an Euler path? So the path must begin at one of the odd degree vertices. So I want to give a remark here that the path must begin at one of the odd degree vertices. So in the example earlier, the solution start at the vertex F. You can also have another solutions where you start the path at E, which is also an odd degree vertex. Now for this graph, you have an Euler circuit. Why is that the case? So again, we're going to calculate the degree of each vertex. For A, the degree is 2. For B, the degree is also 2. For F, the degree is going to be 1, 2, 3, 4. So 4 edges coming out of F. The degree of D is 2. The degree of C is also 2. And the degree of E is 4. So every vertex in the graph has an even degree. You say that sin the degree of every vertex is even, the graph has an Euler circuit. Alright, so where do we start on the Euler circuits? It doesn't matter, right? So it does not matter where you start for an Euler circuit because they are all even degree vertices. So here I want to conclude that it does not matter where you start. Alright, so let me give you a few more examples here, and one of the example is you go back to the example at the beginning of the video where you want to solve the problem of 7 bridges of the Tower of Königsberg. Okay, so the questions for the 7 bridges of the Tower of Königsberg is that is it possible to plan a walk so that you cross each bridge once and only once and return to the starting point? So that is an example of an Euler circuit. Now what we do is that we're going to calculate the degree of each vertex in the graph. So for C, the degree is 3 because there's 1, 2, 3 edges coming out of C. For A, you have 1, 2, 3, 4, 5, so the degree is 5. For B, the degree is 3, and for D, the degree is also 3. So it doesn't satisfy the Euler path and circuits theorems. Therefore, it is not possible to plan the walk so that you cross each bridge once and only once and return to the starting points. So it's not possible. This is the solutions given by Euler in his paper published in 1736. Okay. We're going to move on to some more example to help us identify if the graph represents an Euler path or an Euler circuit or neither. So for this example, I want to know if there's an Euler path, Euler circuit, or neither. So what I want to do by looking at this is that first I need to calculate the degree of each vertex and then use the Euler path and circuits theorem to identify if I have an Euler path or Euler circuits. So for the first graph, the degree of the vertex A is going to be 2. For B, the degree is 2. For E, the degree is 4. For D, the degree is 2. And for C, the degree is 2 as well. Therefore, the first graph has an Euler circuit. So there should be multiple solutions to the Euler circuit for this graph. So one of the solutions is going to be, so I'm going to start at the vertex A. So you go from A to B to E, go to D, and then go to C, then go back to E, and then go back to A to complete this circuit. And if you fill in the edges, so E1, E2, E3, E4, E5, and this is E6. And you see that the Euler path travel every edge once and only once and start and end at the same vertex, and therefore is identified as an Euler circuit. Now for the second graph, we're going to calculate the degree of each vertex in the graph. So at A you have 1, 2, 3. So the degree of A is 3. The degree of B is also 3. The degree of C is 3. The degree of D is 3 as well. And the degree of E is 4. So it does not satisfy either the Euler path and circuit theorem. So there's neither Euler path nor the Euler circuits. Now for the last graph, you calculate the degree of each vertex as well. So for A, you have the degree to be 3, B, the degree is 3, E, the degree is 2, D, the degree is 4, and C, the degree is 2. So there are exactly 2 odd degree of vertices, therefore satisfying an Euler path. So since there are exactly 2 vertices of odd degree, the graph has an Euler path. So what vertex should we start to write out the solutions for the Euler path? Again, you start at either A or B because they have an odd degree. You go from A to C, from C to D, from D to E, from E to B, from B go to D, from D go to A, and from A go to B, to travel all the edges once and only once. And the edges that the U is going to be, so A go to C, that's E1, C go to D, that is E2, D go to E, E3, E go to B is E4, B go to D is E5, D go to A is E6, and A go to B is E7. So that's it in terms of the Euler paths in Euler circuits. So I want to also mention something that the Euler paths in Euler circuits are going to be particularly useful for certain real-world applications. For instance, for checking parking meters along the street of a city, or patrolling the street of a city, or delivering mail, or picking up garbage. So that's it for me. In the next video, I'm going to talk about Hamiltonian paths in Hamiltonian circuits.